Hello and welcome back to the course on deep learning. Today we're kicking off this section for recurrent neural networks, and I'm very excited about this section. There's going to be quite some interesting tutorials. This is one of the most advanced algorithms that exists in the world of supervised deep learning. So let's get started. We have our little breakdown of supervised versus unsupervised deep learning branches, and here we've got artificial neural networks, which we've already talked about. We've already talked about convolutional neural networks as well. And today we're talking about recurrent neural networks. So that's just so that we see where we are in the big picture of things, slowly getting to the unsupervised part of the course. But nevertheless, let's focus on RNNs today. All right, so now that we know where we are on the map in terms of a list, let's have a look where we are on the map in terms of the human brain. And so why are we doing this? Why are we looking at the human brain as if it's a map of the world? Well, the reason for that is the whole concept behind deep learning is to try mimic the human brain and get kind of similar functions as the human brain has and leverage the things that evolution has already developed for us. And I thought it would be pretty cool if we can somehow link the different branches of deep learning that we've discussed. So we've talked about, or the algorithms that we've discussed, we've talked about ANN, CNN, and now we're talking about RNN. If we could link those to certain parts of the human brain, and if it would make sense. So let's have a look. Here we've got the brain, the human brain. It's got three parts. So we've got the cerebrum, which is all of this colored part. Then we've got the cerebellum, which is underneath there, and that's the little brain. I actually looked it up in Latin. That does mean little brain. How funny is that? And we've already looked at a dissection of the cerebellum in the part where we were talking about ANNs, that orange, that big, remember that big orange picture where we saw all of those little neurons and we were trying to kind of gauge how many there are there. There's millions of neurons in the brain. And then we've got the brain stem over here, which connects the brain to the organs and arms and legs and so on. And so that's how the brain, or those are the main three parts of the brain. Now, the cerebrum has four lobes, and they're colored in here. So it's got the frontal lobe, it's got the temporal lobe, it's got the parietal lobe, and it's got the occipital lobe. And now, how do we link these, right? So we've got ANN, we've already discussed CNN and RNN. And the hardest one probably was to start off with ANN, because what is the main advantage of ANN? Well, the main advantage, the main breakthrough in ANNs is, apart from the backpropagation algorithm, which kind of applies to all of them, and in fact, whatever applies to ANN applies to everything here. But for me, I think the main thing about ANNs, and it wouldn't even exist without this thing, this whole concept of deep learning wouldn't even exist, are the weights. The fact that ANNs can learn through prior experience or through prior epochs and prior observations, that's extremely valuable. And so what do those weights represent? And moreover, the weights, of course, are present across all neurons in the brain. But we're going to try to take away the main philosophical underlying notion there, and that is that weights represent long-term memory. That once you run your ANN and you've trained it, you can switch it off, you can come back later, it's trained up, you know the weights, and so whatever input you put into it, it will process it the same way as it would yesterday, as it will tomorrow, as it will the day after. So the weights are long-term memory of a neural network, and that's why weights, or the ANN, go into temporal lobe. Again, the weights exist across the whole brain, but philosophically, ANNs are a start to deep learning and they represent long-term memory. So we're going to put them in the temporal lobe because the temporal lobe is responsible for long-term memory. That hence it's called the temporal lobe, meaning things last through time in there. Brain is very complex, and of course other parts are also responsible for memory as well, but we're going to simplify things and say ANN is like the temporal lobe. Then CNN is much easier. It's vision, recognition of images and objects and so on. So that's the occipital lobe. And today we're talking about RNNs, and as you'll find out, RNNs are like short-term memory. They can remember things that just happened in the previous couple of observations and apply that knowledge going forward. I'm giving away so much already. You pretty much know the rest of this tutorial, but nevertheless. So that's the frontal lobe. That's where we have a lot of the short-term memory, and of course the frontal lobe also, like a quick breakdown. The frontal lobe also is responsible for personality, behavior, motor cortex, working memory, and like lots of other things. But in our purposes, the main thing that we're looking out for is the short-term memory. By the way, if you're interested, temporal lobe is concerned with recognition memory. That's our long-term memory. Parietal lobe these are from Wikipedia. The parietal lobe is responsible for sensation and perception and constructing a spatial coordination system to represent the world around us. And we are yet to create a neural network which would fit into that category. And occipital is vision. All right, so there we go, a bit of neuroscience. So let's move on to our favorite neural networks. So here we've got a simple artificial neural network, 3 inputs, 2 outputs, 1 hidden layer. What does a RNN do? How do we represent or turn this into an RNN? Well, we squash it. We squash it all together. So they're still there, but we think of it as if we're looking from underneath, from underneath this neural network. So we're looking at a new dimension, right? So we're looking, it's still there. It's just flattened out. We're looking at we're adding a new dimension to all of this. But remember that those neurons, the whole network is still there. Nothing changed. We just squashed it for our purposes. Then to simplify things, we're just going to change these multiple arrows into 2. Then we're going to twist this whole thing, make it vertical because that's the standard representation. Then in terms of neural networks, we're going to color them, instead of green, we're going to color the hidden layers in blue. And there we go. And we're going to add this line. And what does that line do? Well, that line is the temporal loop. And this is an old school representation of RNNs, and basically means that this hidden layer not only gives an output, but also feeds back into itself. So again, this is an old school representation. So the common kind of approach is now to unwind this or unroll this temporal loop and represent ANNs in the following manner, like that. So you can see that, again, don't forget that we've got lots of these things happening, right? So you're looking in a new dimension, that the layers are actually still there. They're still there, but we're just not focusing on them. We just remember that each one of these circles is not one neuron, it's a whole layer of neurons. And so what is happening is you've got inputs coming into the neurons, then you got outputs, but also the neurons are connecting to themselves through time. So that's the whole concept, that they have some sort of memory, short-term memory, that they remember what was in that neuron just previously, and then the one before that before that it used to remember what was previous. And that allows them to pass information onto themselves in the future and analyze things. Kind of like when you're watching this course, right? So it would be very sad if you could not remember what was happening in the previous tutorial, right? Even if we break time down discretely through, not by seconds, but like continuously by seconds, but discretely through tutorials, and we say like every moment in time is a new tutorial, it would be very sad if you did not remember what we had in the previous tutorial, or in the previous section, or in the previous part of the course, right? Because then this whole recurrent neural networks part wouldn't make any sense. You wouldn't have memory of what a neuron is, what an activation function is. But because you do remember those things, you can understand this. And same thing here. So why would we deprive a artificial construct which is supposed to be a synthetic human brain, or like mimicking the human brain, why would we deprive it of something so powerful as short-term memory? Long-term memory is great, but short-term memory is so powerful, why would we not give it that opportunity? And that's where recurrent neural networks come in. That's the gap that they fill in. And so let's have a look at a couple examples. So a huge shout out to the Karpathy blog, karpathy.github.io. Some of these examples are from here. So one-to-many relationship. This is when you have one input and you have multiple outputs. Example of this is an image where a computer describes the image. So you have one input, the image, and that would go through a CNN, and then it would be fed into an RNN. And then the computer would come up with words to describe the image. And this is an actual computer describing image. How accurate is that? Black and white dog jumps over bar. This is a computer looked at this image and it was like, oh, it's a black and white dog. Based on what it's previously learned, the long-term memory allowed it to come up with weights and come up with certain feature recognition system, and come up with the filters, come up with everything that is required in a CNN. And then the RNN allows it to make sense out of the sentence, right? So you can see that the sentence actually flows. There's an and, there's a like over the bar, and then there's like a verb, there's a noun, and so on. So basically the RNN is what allows it to put a sentence together in this case. Then many to one an example would be sentiment analysis. So when you have a lot of text, and from that text you kind of need to gauge, is it is this like a positive comment or is it a negative comment? What's the chance that it's a positive or how negative is that comment? And you've got an example here as well. And again, there's lots of other different examples. These are just some. Then we've got many to many. For instance, I wanted to show you this one. So here we've got an example of Google Translator. And I don't know if Google Translator uses RNNs or not. I know that they have very sophisticated deep learning in Google Mind, and I've heard that they've used that in their Android systems and so on. I'm not sure if they use RNNs here or not, but the concept remains. So if I say here from English to Czech, I say, I am a boy who likes to learn. Jsem kluk, který rád učit, right? And basically, in some other languages, it is important what gender your person is, right? So here, boy is male, so that's why it's got který rád. And if I change this to girl in English, the other words don't change. But in Czech, the other words change. Jsem holka, která ráda se učit. So you can see right away, now it's not který rád, it's která, meaning that these words, they depend on the gender of this word, holka. And holka is a girl, and therefore this becomes která ráda. And again, I don't know if Google Translate uses on RNN. I'm not going to comment on that, but basically the concept is the same, that you need short-term information about the previous word in order to translate the next word, right? You can't just translate word by word. It's just a simple example, and of course, to make a sentence make sense, you do need information about the previous words. But like a very visual example we have here is that at the least you need to know the gender of this word in order to translate the following words for the sentence to make sense. And that's where RNNs have power, because they have short-term memory, and they can do these things. So there we go. That's a many to many. You put in lots of words and then you get lots of words out. That's translation. And of course, not every example has to be related to text or images. There can be lots and lots of different applications of RNNs. For instance, many to many, you can use RNNs to subtitle movies, meaning that you can have running subtitles, so basically, or describe every single frame in a movie, and that is something you can't simply do with a CNN or other neural networks, because if you're watching a movie, you need context about what happened previously to describe what's happening now. And so you need that short-term memory. You can't just run through a million movies and kind of understand the whole plot that is going to happen. You need short-term memory of the plot to be able to comment on every single frame. And speaking of movies, today we don't have additional reading. Today we have additional watching. So a movie called Sunspring in 2016, directed by Oscar Sharp, and it's got, you might know this actor Thomas Middleditch from TV show Silicon Valley. And this movie was entirely written by Benjamin, who is a RNN, an LSTM to be specific. So I'm going to show you this movie now. Well, I'm not going to play it. I'm just going to show you where to find it. So you need to go to Ars Technica. It's only 9 minutes long. I highly recommend it. I've seen it twice. It's so fun. Like you will find that. So a couple things. There's a great description here as well. So it's worth reading through it. There's actually an interview of Benjamin, and he actually gave himself the name of Benjamin. That's why they call him Benjamin. It's just really cool to see these things. And what you'll find about the movie is the acting is amazing, just amazing. Like I had shivers down my spine towards the end. It got in the top 10 in the London in the London Sci-Fi London Festival. And then what you'll find is that Benjamin is able to construct sentences which kind of like make sense for the most part, which is good. But what he lacks is kind of the bigger picture. He cannot come up with like a plot that constantly makes sense. Even though the actors do a great job about putting it together, and it does look amazing in the end. But you will notice and kind of look out for this. When you're watching, separate the sentences, and you'll see that each sentence on its own, more or less 90% of the time, makes sense. But overall, he cannot properly link sentences together. And that's the next step for RNNs, where this is still quite a new technology, or it's only picking up recently. So it'll be developed very soon. And maybe when you're watching this tutorial, you're laughing in the future, 5 years from now, you're laughing to yourself and you're saying, oh yeah, we've already passed that milestone. And probably we will very soon. But this is where things are now, and highly recommend checking this out. Only 9 minutes long. So there we go. That's what RNNs are in a nutshell. And in the next tutorial, we will continue digging deeper. I look forward to seeing you next time. Until then, enjoy deep learning.